Alright, welcome back everybody. So we're going to finish up talking about the different groups, and then we're going to move on and talk about some of the terms that you really need to know. I kind of mentioned them a little bit, but we're going to get into more detail. So last time we left off with group 2, talking about how they form +2 ions, how they're very similar to group 1, not quite as reactive because they tend to have a slightly greater pull on their electrons. They're less likely to let them go when they react with another element. Most of them are found in types of ores. That means, in rocks and minerals, they need to be isolated and purified. Now, group 17, these are called the halogens, as I mentioned before. And group 17 has some interesting properties. First of all, they're the most reactive nonmetals. Something like fluorine, for example, it is the most reactive nonmetal, period. And what's also interesting about these halogens is that they have all three phases. So fluorine and chlorine are gases. Bromine is a liquid. And iodine is a solid. Notice they're all diatomic. And notice I don't really talk about astatine, and that's generally because astatine just isn't really considered one of the alkali metals. They just don't consider it, one of the halogens. Okay, so let's talk about group 18. So these are called the inert gases or the noble gases, and that's because they generally don't react. So part of the reason why they are non-reactive is because they have very small radii when you compare them to other elements, and they have very high ionization energy. So it's very difficult to remove an electron from one of these atoms. And they're not going to gain an electron, and maybe you could think about why. Why won't they gain an electron? We could talk about that in class as well. So you've heard about the diatomics before down here. What makes them diatomic? It's two atoms together. And I call them the, Brinkelhoff gang, as some of my students already know. I won't call you by name. So these 7 elements all exist as diatomics, two atoms bonded together. There's also some other great, forms of elements, like carbon, for example. It can take forms of 60 carbon atoms, something called a Buckminster fullerene or a buckyball. And this is a cage-like molecule. And people are really trying to exploit this, trying to put other molecules inside the cage, use it as a delivery system. But carbon also could be in the form of diamond, graphite, and even something called graphene. We'll talk about all of these when we do types of solids and bonding. Sulfur, for example, can also exist as 8 sulfur atoms together, and phosphorus can exist as 4 phosphorus atoms together. So sometimes atoms, they just bond with themselves, and that makes them more stable. So radioactive elements, although we're going to do a chapter on radioactivity, and you've seen this before with Regents chemistry, you might already know that any elements that are 84, that's atomic number, or higher, is going to be radioactive. It's not stable. So these are just some fun facts about the elements. Let's get into talking about, really important things like what makes an atom behave the way it does. What do I mean when I talk about in terms of atomic structure? And so the first thing that I'm going to talk to you about is nuclear charge and effective nuclear charge. And nuclear charge, it's just the number of protons. And this makes sense. Protons are in the nucleus. Protons are the only thing charged in the nucleus. So if you have, sodium, for example, sodium is going to have, a nuclear charge, or a Z, equal to 11. So nuclear charge gets the symbol Z. Now, before I do effective nuclear charge, I want to talk to you about shielding, because we're going to mention shielding in effective nuclear charge. So what shielding is the number of core electrons that effectively block the attractive force the nucleus has on an atom's electrons. So, you know this as energy levels. As you add more energy levels of electrons, those effectively inhibit or shield the pull that the nucleus has on the valence electrons. So how does this play into something called effective nuclear charge? Well, effective nuclear charge, called Zeph, is actually equal to the nuclear charge minus the number of shielding electrons. So if I were to look at something like, sodium again, with its 11 protons, and if we just look at energy levels 2, 8, and 1, we can calculate the Zeph for each of those. And so if we were to do that here, the 2 electrons right here, they feel as though there's 11 protons pulling on them, and there's no shielding electrons. So their Zeph is actually going to be plus 11. They are very, very tightly attracted to the nucleus. If I look at these 8 electrons, well, these still have 11 protons pulling on them, but now we have minus 2 inner core electrons blocking them, and that gives them a Zeph of plus 9. And if we look at this outer electron here, this is 11 minus 8 and 2, so minus 10. So this has a Zeph of plus 1. So the pull on that last electron is much lower than the pull that's on the core electrons. These are considered the core electrons. When we look at sodium and we say, well, what ion does sodium form? And it's a plus 1 ion. Well, that occurs because those inner electrons are much more attracted to the nucleus and feel a much stronger attraction and pull to it. And so the energy required to remove them is much, much greater. So there is partial shielding that occurs, and there's a more complicated equation that we can apply because we can look at sublevels. However, I'm not going to do that with you right here. If you want to talk about it, we could talk about it in class. And the last thing I want to tell you about with respect to atomic structure is electron-electron repulsion. And so electron-electron repulsion, this is where the electrons repel each other because they're the same charge. And this, this basically what it does is it pushes the electrons further from the nucleus. So if we look at the first energy level, n equals 1, we can fit 2 electrons. And that's because this is a very small energy level. When we look at n equals 2, you can fit 8 electrons. The energy level is larger, so the repulsions can be minimized more. You can fit more electrons in there. Energy level 3, we can fit 18 electrons. Even within energy levels, though, we'll see that we have repulsions. Like, for example, if I were to look at repulsions in the p orbitals. So when I have my p orbitals, I can fill them up 1, 2, 3. And this would be an ideal situation because repulsions would be minimized at this point. But what if I were to go ahead and start pairing them up? Well, as soon as I start pairing them up and putting in here 4, 5, and 6, the repulsions get greater. So whenever you try to pair up electrons, you're always going to get a greater repulsion. The question is when we start looking at all of these factors together, so how does the nuclear charge either, overtake the repulsions or the repulsions overtake the nuclear charge? How does the shielding play in a role? So these things all kind of come together, these 4 ideas. Now, what do? Well, they affect the properties of the atom. And these are the 4 definitions that I want to go over today before we stop. Atomic radius is generally just the distance between the nucleus and the valence electrons. Ionization energy is the energy required to remove the most loosely bound electron from a gaseous atom. Electronegativity is the attraction an atom has for electrons in a bond. So electronegativity only applies when you're bonded. And then finally, electron affinity. This is the energy change, and it could be positive or negative, when an atom gains an electron. Now just to really quickly to wrap this up, talking about some of the units, atomic radius is normally in picometers. Ionization energy is normally done in kilojoules per mole. Electronegativity has no units. It's on a scale of 0 to 4. And electron affinity is normally on the units kilojoules per mole. Ionization energy is always positive. It's always endothermic. Electron affinity could be positive or negative. We'll talk about each of these and their trends in the next video. All right, thanks so much for watching.